Good morning, and I've returned here at the Radisson JFK airport. That is the Radisson Hotel, JFK vicinity. Dolphy Gilpin is your host here, doing some video lecture on the amazing 5x12 matrix. And this time we're moving into the more advanced application, the electronics engineering application. And we will, at this moment, we won't be, we'll return to the easier 2x2 mesh circuit, but we're going to start off with some 3 mesh circuit. We're going to start off with some 3 mesh circuit. And so let's draw some model 3 mesh circuit here. Some modern 3 mesh circuit model could look like so. It's some form of power source here. We have some resistance, simpler type here, a power source, and let's deal with some real life situation, about say 480 volts here at this power thing here. 480 volts, we've seen it many times in our elevator, powering the voltage of a horizontal moving escalator, or even the elevator, 480, 960 volts. So we're going to be dealing with some real life situation here, at least for the voltage side here. At least make one of the parameter to it. And then we're going to move in some smaller numbers to make our application easier with the resistances. And say we choose now 0.5, and I'm using this number. It could be just 5, but I'm maintaining this dual thing to make it look more real like the PDM application. And say we choose 0.2 here, and I'm making these very small for ease of computation. 0.4, 0.1, and say 0.3. Now what I'm going to be doing, I'm going to from my inspection, formulate my 3x3 matrix from this, from inspection. But I'm going to use some small values. I'm going to just drop down some what it could have been, the real numbers here. Could be dealing with some numbers like 55 here. Say this like it would be like 24. I'm just making up some numbers here, 40. Or 34. 55. So it could be like 11. Let's say this one's like 33, which I'll make them very simple. And so we're going to move into even some of our terminologies would be advanced. And we're going to move into, say, delta. We call this now delta is equal now to, and we formulate our 3x3 inspection. And this is now mesh 1, mesh 2, mesh 3. This is one of the easier 3x3s now. And so for mesh 1, we have now R11 And notice we move back into some general thing here. And we're going to be using not absolute values now, but the real values. And the next one will be R12. And you notice I drop in the minus sign here, but this second element here is a negative. And this is now R13. And this is a positive. Next one will be R21 here. And this is a negative. And this is a R22 positive and R23 negative. And this one is a positive, which is R33. So it's a negative R32 and R31. Notice positive, negative, positive. Positive, negative, positive, negative, positive, negative, positive, negative, positive. They're no longer absolute values, without the sign values. No, they are taking on real values with signs. Furthermore, we'll note also, I'm telling you these things, but most of the time I'm writing them down and you're going to see some sign changes, that the mutual resistances take on a negative as well. The mutual resistances. And so we say delta is now the determinant of this matrix here. And that's equal now to R11 into R22 minus R23 minus R32 plus R33. This is a positive R1. And if we're coming down the column here now, we'll say now minus R21 minus R12 plus R13 minus R32 plus R33. Delta, the determinant of the source, 3 by 3 here. We'll find some numerator values, and then we'll see how it's applicable to this answer. So R31 plus minus plus R31 into minus R12 plus R13. This means the first column, the second row, or the first column, R31. This is the third row, first column, R31. Let's see to the second R12, which was the same row here, but different columns. R12, the first row and the second column. So R12, R31. See, when I move on to explanation, it really takes up the time. But the advanced electrical electronics engineering student would know these things, and the mathematical advanced people would know these things. So we have now R12 R31 into minus R12 plus R13 plus R22 minus R23. And so if we move on over, we'll get now minus R32 to R11, R13. And if I don't put a sign, it means positive. And if I don't indicate a sign, it means it's positive. So we'll deal with R32, which is a minus. And these are 21. So that will be R22. Remember I'm saying these things, the mutual resistances are negative, as well as this is a sign. And there's a way to calculate the signs of these elements of the matrix. But for now, we'll just say that if this is the first row and first column, then if you say 1 and 1 is 2, it's even, then all even elements take on a positive, and all the negative are the uneven numbers. So we add 1 and 2 here. Same row, different column, 1, 2. All these are 1, 1, and 1. The same, different columns now, 2. This is column 2. And column 3. So here we are now. R12, if we add the 2 and the 1, we get 3, so it takes on the negative. If we add the 1 and the 3, it's even. 3 and 1 is 4. It takes on a positive. So choose this one, 3 and 2, 5. It takes on a negative. So the even thing when you add the sub or the superscript, which is the rows of the column thing, if it's uneven, it takes on a negative. So that is one way of determining the signs of the elements here. It's also another exponential way to calculate it. But we are going to stop to simplicity right here. And notice that we move away from the absolute values of the elements into the real values that the elements take on. So here we are now, R21. And we are calculating delta, which is the determinant of this matrix, which is a 3x3 dual period in an algebraic form. So we have R22 now. Very good. R11 plus R31. R11 plus R31. Whenever I don't put a positive, it means that it's a positive. R13 and R33. Next one is minus R12. The determinant of this matrix I'm calculating here now. Minus R12. So leave it R21, which is a negative R21 here. Minus. Okay, negative 2, 3. Positive 3, 1. And a positive 3, 3. R13, positive R13, so negative R21, positive R22, negative R31, and negative R32. Negative R23, this is all taking the determinant of this 3x3 matrix here, the source 3 by 3. And this is without regard to the mutual sign of the elements in the mutual resistances. They take on a negative sign. All the mutual resistances take on a negative sign. So we have minus R23. We are generating the R13, then this is R23, negative R23, into R11, R12. The sign of this R12 is a negative, positive R31, a negative R32. And so the last one in this determinant would be full-blown determinant, not partial, but full, and it's now plus R33 to R11, R12, disregard this here for the moment, R133 is R11 minus R12, R21, negative R21, and positive R22. So that is the determinant of this matrix, we call it delta. And sometimes you have to differentiate between delta. If you look like so, with a base from del, which look like so with this is del, and this one is delta. One with the point here, the apex down, and one with the base down. Del and del. Alright. So the determinant delta we call it. And if we should expand this out, we get now that's equal now to R11 into R22, R33, that's all positive, R22, R23, R33 rather, minus, and I'm going to be doing some of this thing in my head because you multiply these two, then subtract it, you're going to get 3 negatives, which brings us back to a negative, minus R32, R23, right? Because you multiply this, and then you subtract it. It gives a 3 minus sign there, which is a negative. This will be a minus R21 into, multiply these two, negative and positive is negative, R12, R33, this take on a negative sign there. Multiply this and this to get a negative, and you take the negative, it gives you a positive. So first of all, it's a positive. R13, R32. We're finding the determinant of this source matrix here. We are saying that the elements we want to maintain a dual digital for the elements, which is not to say these 1 here, it means rows and columns. First row, first column, first row, second column, and first row, third column. Second row, first column, second row, second column, and second row, third column. Third row, first column, third row, second column, and third row, third column. That's what these subscripts here mean. Alright, so we are finding the determinant and we're continuing now. That's just for these two. Come on to this one is with a positive R31 into multiply these two. Minus and minus give you positive. We get now a positive R12, R23. Minus is a positive. And we subtract now. This is a positive R23. Sometimes we have to revert back here to make certain 23 was negative here. Calculating here this one. So it's R31 and into now two negatives make a positive. R12 and R23 positive. We're subtracting now R12. This is R31 matrix. This is a minus R12 here. Yeah, this is a minus. And what about this one we're doing? 3, 2. R31. This is a 1. Because R12, R23. R12, R23 takes on the minus R23 here. This is right. And the minus R12 and the plus R13 and the plus R22. R3, R12, R23 and R13. Oh, this is 13 and 22. And this is plus 13 and a plus 22. Okay, so that's clear up the ambiguity there with the signs. So we have now R31, R12, and R23. Two negatives is a positive, right? Subtracting now plus, and minus, plus and plus give you minus. So we get R13, R22. Move over to this one, so we got minus now R32 into minus R11 R23. And maintain this minus sign there. And it is minus, which gives us a plus R13 R21. We multiply out this thing is to get back into a minus here. Minus R32 into this gives you minus. Minus and minus multiplication gives you a plus. Okay. And this one will be now plus R22 into R11 R33 minus R13 R31. And this one here now would be minus R12 into, bracket just here is the multiplication sign. Minus 7 plus give you minus R21 R33, and minus give you a plus now R23 R31. Move over this one, this is a positive now, R13 into, and this 2 negative here positive, R21, R32, and this now, negative and negative give you a positive. This is a negative 31 here. So we get now a positive R22, R31. And we're finding delta, which is the determinant of this matrix. This one now would be minus R23 into minus R11, R32, and 2 negative here would be a positive, plus R31, R12. This would be plus R13 into R11, R23, positive, R11, R23, minus, minus, and minus, give you a minus, minus R12, R21. You have terminals now, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have generated all of this. So that's the determinant. We further now have to go out and subtract these, multiply this R11 into R22, R33, minus that. And that will give us the value of that determinant from first principle. We'll be dealing with numbers here, but now we're just dealing with the general. So that's the determinant there. Then what we'll do, example, we'll be applying Kirchhoff's law. So what we'll have here, we're going to replace, say that now, some voltage V1, or let's use here, we call this V1, and say for mesh 1, and say V2 for mesh 2, and V3 for mesh 3, mesh 1, mesh 2, and mesh 3. We note we have chosen 480 for this, really. I want to bring in some real life situation voltage here. This makes something look real here. That is a voltage, say, at a horizontal escalator, power in a horizontal escalator. Power is equal to V times I. And we'll be moving into some complex operation with which we're going to see some real imaginary and real numbers thing. But for right now, this one is that. We'll bring on the inductance. We'll see that. We'll calculate real power and complex power and so on. And give some phase angles for current and voltages. All right, so this is the determinant. And say, for example, now we have, let's say that for V1, V2, and V3 here. In this case, V1 in this case will be 480 volts, but I'm not dealing with the algebraic form right now. V is equal to IR. So we have RI rather. So we'll have now R11 minus R12 plus R13 minus R21 plus R22 minus R23 plus R31 minus R32 plus R33. Consider the mutual values of resistances that going to have some change signs in these, but let's just keep it at that for the moment. V is equal to Ri, and so our I values now would be I1, I2, and I3. So this is just Kirchhoff's law. Voltage is equal to current and Ohm's law. V equals IR. Voltage